Uh, Welcome to the discussion of tutorial 2, that is T2. This is your tutorial and second tutorial we are discussing today. I will be discussing question number 2 and 3, okay, in this continuous video. There will be further videos for question number 4 and 5. Question number 1 is supposed to be solved by yourself. It's just a direct substitution of relation between spherical polar coordinates. I mean the transformation equation from spherical polar coordinate system to Cartesian coordinate system. So you can directly apply it and solve it. So it's just a mathematical only mathematical steps are algebraic steps are involved in it. So therefore we will not be we don't have to understand we don't have to discuss it now. Okay. The rest of the problems has some kind of physics involved in it, so therefore I will we are thinking to give you some insight into it. A complete solution, step-by-step solution may not be there. There will be, but the idea we are trying to communicate the physics behind physics of this question to you. So let's look at the question number 2. It's there on the screen, as well as you have the question paper with you. So look into it. We have a compact aircraft P takes off at A with the initial speed of 100 meter per second in the vertical plane y dash z dash. You have the figure. Making an angle 30 degree with y dash axis. It maintains a constant acceleration 2 meter per second square along its flight path. Obtain the position and velocity of the aircraft in Cartesian and in cylindrical coordinates as measured by the radar at O. 60 seconds later it took off. So the question is pretty clear and straightforward. You can see that there is a radar here. It's at 3 kilometers away, so there is the distance from the radar and the takeoff point is already given, that is 3 kilometers. The angle of takeoff is given, that is 30 degree. Now you have the initial velocity given v0, that is given already, is equal to 100 meter per second. So that part is given. Acceleration is given 2 meter per second square. Then the time is given 60 seconds. What else is given? That's the angle that it makes PAQ. Let's say this is Q, so let's say PAQ is given, angle PAQ is given as 30 degree. So basically we have everything that is required to calculate. So let's see what is each points, that is OA. So OA, you know, it is equal to 3 into 10 raised to 3 meters. Since it is 3 kilometers, so 3 into 10 raised to 3 meters. Now we have this, we can calculate this AP, this distance from A to P, you can easily calculate. To calculate that, we can use kinematic equation 2, that is UT plus half AT square. Using this you can find out here U is V0. So V0 is simply 100 into 60 plus half into 2 into 60 square. So this is your AP distance AP, which is equal to, I will give you the direct answer, 9.6 into 10 raised to 3 meters. That is your AP. So the distance it covers in 60 seconds we already got, that is 10.6 into 10 raised to 3 meters. That is what the flight takes in 1 minute. Okay. So once you know AP, you can find out what is AQ. AQ is simply AP cos 30 degree, since this angle is 30 degree. So that value is equal to that value is equal to 8.3 into 10 raised to 3 meters. Then you can, in the similar manner, you can calculate what is this distance PQ is also. So distance PQ you can calculate, which is equal to AP sin 30 degree, sin 30 degree. So this sin 30 degree, which is equal to which gives a value 4.8 into 10 raised to 3 meters. So we have everything we require to calculate, give the Cartesian coordinate system here. So the Cartesian coordinate system, how will you find out? Now we have to find it out with respect to O. So let's draw that Cartesian coordinate system here. with respect to the radar. So if you draw that Cartesian coordinate system with respect to radar, this is your Cartesian coordinate system, let me denote axis, all the axes. So x, y and z axis we have. So this radar is at O. Now with respect to the Cartesian coordinate system, this point A is our where from the flight is taking off. So let me draw the YZ plane there is taking off. Now this is the taking off. So let's draw the path at which it takes off. Let's say this is the path it takes off. Now let me denote the axis properly, y dash and z dash. This is the angle 30 it makes, angle 30 degree it makes with y axis, and let's drop this Q here. So therefore this is the point P. So P has coordinates z, y and x, y and z. So what is the x axis? This distance is your x coordinate, this distance is the y coordinate, and this distance is the z coordinate in the with respect to the radar. So all these values we already calculated here. So therefore we can write P x y z as P x cap. What is x cap here? That is OA. OA we already calculated above. So that OA is 3 into 10 raised to 3. So 3 into 10 raised to 3 meters. You don't have to put meters there, it's the coordinates. Then you have y axis as AP cos 30, that is S 8.3 into 10 raised to 3, and you have then z axis as 4.8 into 10 raised to 3. So you have all the coordinates here. Now what the second in the question what you have to calculate is the velocity. So how to find out the velocity in the Cartesian coordinate system? First we can find out the magnitude of the velocity, that is v. You can find out from v naught plus at. This is the first kinematic equation. So using this, v naught is 100, 2 into 60, which is equal to 220 meter per second. This is your velocity, magnitude of it. So since this is the velocity, magnitude of the velocity once you know, so the y-axis you can whatever the components of velocity along y-axis you can find out from v cos 30, and similarly manner you can find out the z part, that is v sin 30. So this both you can find out. So therefore velocity v is equal to v cos 30 y cap plus v sin 30 z cap. So the final answer is 190.5 y cap plus 110 z cap. So therefore you have the velocity here. This is the velocity in Cartesian coordinate system. So that part is clear, I hope. So let's look into the what it will be in the cylindrical polar coordinate system. So first let me show you what is the cylindrical polar coordinate system and the transformation from Cartesian to cylindrical polar coordinate in a short discussion. This is already discussed in the class, I'm sure. So let's say this is the Cartesian plane polar coordinate system to the Cartesian coordinate system. So let me denote the axis x, y and z here, and the arrows of course. Now to define a point P here in the cylindrical polar coordinate system, we define the distance from the z axis to that point as the r, and whatever angle it makes with z axis, this angle is the theta, and this distance from origin to here, this distance is your z, therefore you have the coordinates of it, r, theta and z. So this is your cylindrical coordinate system, and theta takes values from 0 to 2 pi because it goes around. So and r takes values from 0 to infinity, and z can take values from minus infinity to plus infinity. That's how the cylindrical coordinate system is defined. Now what are these values for our problem here? So let me redraw the our picture here in the point of view of radar again, with respect to origin as the radar. So this is your O, x-axis, y-axis, z-axis, radar is at origin. Now the takeoff point, let it be here A. So the YZ plane, if you look at it, the YZ plane is here, y dash, z dash, and the taking off. So this is P, and this is Q. So in the Cartesian cylindrical polar coordinate system, now we have to find out our r here. So to look at r, this will be our r from origin to the point q here. This is your r. So now I am denoting my r. This angle is your theta. Let me denote with a different theta. Now this is your z. So z can be measured from pq again. So z we already have it from Cartesian coordinate system. So this is the same length. Okay. All right. So the coordinates are r, theta, and z. So now we have to find out r. What is r? To find out r, you use the Pythagoras theorem. You have, that is under root of OA square plus AQ square. We already know what is AQ and OA. So OA is, we already calculated, it's equal to 3 into 10 raised to 3 meter, and AQ also we calculated as AP cos 30 degree, which is equal to 8.3 into 10 raised to 3. So therefore you can easily find out what is this r equal to. You substitute it there. So r equal to 3 into 10 raised to 3 whole square plus 8.3 into 10 raised to 3 whole square under root. So you, when you calculate it, you have to get the answer equal to 8 into 8.3 into 10 raised to 3 meters. That's your r. Now you have to find out the theta. To find out theta, you use trigonometry, your trigonometric ideas. So that is tan inverse of AQ upon OA. So those values also you have. So it is if you round it, the rounded value is equal to 70 degree. So that's the value of theta. So now you are set. You have theta already, and z you already have calculated, which is equal to 4.8. So z is equal to 4.8 into 10 raised to 3 meters. So you have all the values. So therefore the coordinates of P is therefore in Cartesian coordinate system is equal to r theta, and z is equal to 8.83 into 10 raised to 3 comma 70 degree comma 4.8 into 10 raised to 3. This is the coordinates of P in the cylindrical coordinate system. Now what you have to find is the velocity in cylindrical polar coordinate system. So the best way to find that is use the transformation equation from cylindrical polar, between cylindrical polar coordinate system and the Cartesian polar coordinate system. You have this x cap, y cap, and z cap related to cylindrical polar coordinate system as cos theta minus sin theta 0, sin theta cos theta, cos theta 0, 0, 0, 1 into r cap theta cap phi cap, r cap theta cap z cap. So this is the transformation equation. So now, and you have velocity v equal to 190.5 into y cap plus 110 z cap. You can see from this equation the transformation relation that y cap is equal to sin theta r cap plus cos theta theta cap, and z cap is equal to z cap, and here theta is equal to 70 degree. Substitute it here, substitute back into this equation, you get velocity is equal to 179 r cap plus 65 theta cap plus 110 z cap meter per second. So this is the velocity. These all are rounded values again. It will be nearby these values since I have rounded to find out this answer to a integer form. All right. So this question is more or less done. The key is this transformation equation. This anyway, to find out this velocity in cylindrical polar coordinate system, you will have to use anyway the ideas of your Cartesian coordinate system. Now if we look into the problem number 3, let's we have the question here. There is a small change in the question. That changes here. I already have changed. So let's read the question first. A small bead is bound to move on the cylindrical in the conical helical wire as shown in the figure below. Conical helical wire is shown by a blue color and the bead is shown as the red color that you can see here. Okay, the height of the bead is rising vertically in Z direction by an amount of Zp for every one turn. So one turn means it comes 2 pi degree. Yes, 2 pi radians, not degree. 2 pi radians, when it comes, it is one turn. So the moment it goes around once, Zp amount, it increases in the Z direction. It height basically increases. The ratio of, so this is the change part. The ratio of change in radius to the change in the height of the helix is P. Okay. At the beginning, the position of the bead in cylindrical coordinate system is r equal to r0 and theta equal to 0 and z equal to 0. Find z and r as a function of theta. Second part, the angular velocity of the bead as a function of theta to maintain constant speed s0. Okay, this question seems very simple, and it's a three-dimensional motion in cylindrical polar coordinate system. This is when you look at directly, you will see it in this manner. But you can find something here. What about this motion? Is it actually in the you require all the three coordinate system to define it? We will see that in a moment. Okay, so because this question, just remember, because even though this is a three-dimensional motion, you can actually effectively convert it to a one-dimensional problem and solve it. I will show you what it means and what it means for your rest of the course also. Okay, let's come to that part. We'll come into that part while we solving it. So cylindrical polar, for your reference, your question paper has the cylindrical polar coordinate system, that it's all given here, how it is denoted in Cartesian coordinates. Okay, what are we given? When we look what are we given, it's given that it's the bead was initially at r0. It's not starting from r equal to r0. At initial time it was at some distance r0. Okay, that part has to be kept in mind. Theta equal to 0 and z equal to 0. That is the origin of it. That's where from it is starting. So now, then it's given after each turn, it increases a height Zp. It's a constant height Zp, it's increasing. So the distance between this turn and the final turn, that is Zp. Each turn between each interval is Zp. Okay, that is another thing you have. So let's calculate what is the relation of z and r as a function of theta. How we get it. Okay, to look into that, let's use the first idea that after each turn it increases a height Zp. So from there you can find out the relation of z and theta. So z is your height. So z is somehow proportional to theta, and now I am writing z is equal to a theta. That proportionality constant is a. So now how will you find out a? To do that, I am going to find out 2 points here. Let's say this point is Q and this point is P. Okay, let's say Q is equal to I am just so you know, since we are measuring it in radians, so each complete turn, circular turn, it will take 2 pi radians. So each point can be represented as like in terms of some integers, right? Let's say this is equal, this point is coming after n turns. So let it be Q equal to that height for Q from the base, that height in terms of Z I am writing. So for Q position ZQ, I am writing as the height for the ZQ is equal to a 2 pi into n. So theta I am substituting it as 2 pi n, and P, let it be Zp, which is equal to a 2 pi n plus 1. So you know that P minus Q, if you calculate, it should be equal to Z. Sorry, again this confusion should not be there. So let me take it as R. Okay, ZR. Okay, this position as R. So R minus Q should be equal to Zp. That is the height difference. It should be always constant, which is equal to a 2 pi into n plus 1 minus a 2 pi into n. So which basically equal to a 2 pi. So therefore A you can calculate from here, which is equal to ZP divided by 2 pi. Therefore that's functional form of Z over theta. You can see it here. Okay, so let me remove this part. This okay, so this part I record for the next part of it, part of the calculation. So now we see how the relation of, now we substitute it back. You can see the how the functional dependence of Z on theta is exactly how it is exactly. So this is how you see this Z is a function of theta. Once you know theta, you can find out Z. Similarly, you can find out the relation for R also. It is given that the ratio of change in R with respect to change in the height, that is delta Z, is equal to B. To find out how it's actually changing, I'm going to make it a differential equation, that is dr upon dz. This also I can write is equal to B, because that ratio has to be constant for whatever change it is. So I'm making it limit to be very small, so that I can write in this manner. Okay, if I integrate it, now let's take find out the solution for it. So dr, integration of dr from B integration of B dz, I can calculate it. Now dz, you know what is z equal to, I'm writing it in terms of A only, z equal to A theta. So dz equal to A d theta. Now I can substitute it back here. So if I substitute it here, I have integral of dr is equal to integral of B dz. Now we have to put the limits also. What are the limits it is? So it starts from origin r naught, or at time equal to 0, when the motion is started, it was at r naught, and it goes to r, some distance r. And at the same time, this angle, I wrote dz again here. Let me remove it and write in terms of d theta. Sorry for that. On the floor. So A d theta. Okay. Start from 0. Okay, this is 0 to theta, some angle theta. Let it be to some n2 pi. So if you integrate this one, it will become r minus r naught is equal to AB theta. So therefore r is equal to r naught plus AB theta. This is your functional dependence of r. So r is some another function of theta. So this is what I said. When you look at the problem, even though it has r coordinate, theta coordinate and z coordinate, you basically see this r is some function of theta, the z is some function of theta. So if you write this coordinate system, you can simply write as g of theta, then theta, then f of theta. So you see basically this problem is a one-dimensional problem. There's only one parameter is required, that is theta. This curve is parameterized by the coordinate theta. Alright, so basically this is a constrained motion. The z, r and z is, the motion along r coordinate and the z coordinate is constrained, and it has a dependence on theta completely. So therefore the degree of freedom here is basically along theta, the angle. So the motion can be parameterized with the parameter theta, and therefore effectively this problem is a one-dimensional problem. When the course moves forward, you will be, when we do the Lagrangian formulation and all, there you will learn about this degree of freedom more and in detail, and we'll be doing more problems with respect to that. But keep it in mind how a three-dimensional problem, which is as one like this one, you can completely turn into a one-dimensional problem. You can reduce the dimension using this parameterization. Okay, so this. Let's move to the second part of it. Now you have to find out the velocity. The velocity, in cylindrical polar coordinate system as r dot r cap plus r theta dot theta cap plus z dot z cap, and what's r is equal to r naught plus ab theta. So which means r dot is equal to ab theta dot, and z is equal to a theta and implies z dot is equal to a theta dot. So now therefore you can find out velocity, what the velocity is. Substitute for velocity. When you substitute for velocity, you get AB theta dot r cap plus r naught plus AB theta dot into theta cap. Then z dot, that is a theta dot z cap. This is what your velocity is. Now it's given, it's the second part of the question is asking you to find out the theta dot for some constant. If the constant speed s naught is maintained, what should be the angular velocity theta naught? So which means the magnitude of the velocity is some constant s naught. So let's find out what is this magnitude v, which is equal to ab theta dot square plus theta dot whole square plus r naught plus ab theta dot whole square plus a theta dot whole square under root is your s naught. Now you can find out theta dot. What is theta dot from here? Theta dot is equal to s naught divided by under root of ab whole square plus r naught plus ab theta whole square plus a square. This is your theta dot for a constant speed s naught to maintain. So more or less we have solved this all the second and the third problem. So what is remaining is the first problem only. It is just like I said, the transformation between the spherical polar coordinate system and the r cap theta cap, the Cartesian polar coordinate system, Cartesian coordinate system. And in the next video we have question number 4 and question number 5 also solved. All right, so I hope you understood whatever we discussed here, especially the parameterization part here, how the coordinates z and r are parameterized with coordinate theta, and how this three-dimensional problem is basically for a one-dimensional problem. I mean you can solve it as a one-dimensional problem. So I hope you understood it. If you have any doubt regarding it, please ask it in the comment section or in the group chat. You can discuss there. So enjoy solving and have a nice day.